Hello everyone. Today we are solving GATE question paper of 2023 and we are taking analog electronics as a first subject. So let's start the video. Question number 1. For the op-amp circuit below, the gain V0 by Vi will be. In this circuit if we see there are three op-amps and op-amps has a property that it is having very high gain. Due to high gain, it follows the virtual ground at this node and virtual short at this node. Here also virtual ground will be there. So we number the op amps. This is number 1 op amp, second and third. The voltage at this node, let's assume it is V01. The voltage here, let's assume V02. The op amp here Here the op-amp is in inverting feedback configuration. Here the op-amp is non-inverting feedback configuration. So let's analyze the op-amps individually. So first take this circuit. This is the negative feedback configuration. The gain of this op-amp circuit will be V0 1 over Vi will be equal to minus R2 by R1. Op-amp number second is in non-inverting feedback configuration. So the gain of op-amp second will be V02 by Vi is equal to 1 plus R2 by R1. So the voltages here and here we have got it. This op-amp is also having virtual short at this node and we are having two voltages V01 and V02. So let's apply the superposition principle for these two voltages. So for V01, by assuming V02 is equal to 0, for V01 by assuming V02 is equal to 0, if this node is virtual ground, so this will be 0 volt. The output voltage here due to first voltage source V01 will be equal to minus R4 by R3 into V01 for V02 by assuming V01 is equal to 0. The output voltage due to V02 will be equal to minus R4 by R3 V02, because here is the virtual ground. So consider this as an active voltage and this as a 0 voltage. This branch will be eliminated. If we consider this as an active voltage and this as a 0 voltage, this branch will be eliminated. Again the op-amp will be in the inverting feedback configuration. Accordingly the voltage V01 due to V01 as an active voltage will be equal to minus R4 by R3 times V01, and for the other voltage V02, the V02 dash, which is the output voltage due to V02, will be equal to minus R4 by R3 times V02. Now the total voltage will be equal to minus R4 by R3 times V0 plus V02, which will be equal to minus R4 by R3 V naught 1 is equal to minus R2 by R1 times Vi plus V naught 2 is equal to 1 plus R2 by R1 times Vi, which will be equal to minus R4 by R3 times Vi. Now the gain will be equal to V naught is equal to minus R4 by R3 times Vi. So the gain will be equal to V naught by Vi is equal to minus R4 by R3. So the option C is correct. So let's go to the second question. Find the output voltage V naught in the circuit. If we see closely, the circuit is nothing but a current mirror circuit, and the current mirror circuit is having very beautiful property that it mirrors the current. Let's take a simple basic. This is, let's assume, I reference current. The current in this branch, let's assume it is I naught. These are two MOSFET having W by L ratios respectively. Now this MOSFET M1 is in saturation mode because the voltage VDS is equal to VGS. If VDS is greater than VGS minus VT, the MOSFET is in saturation. If this MOSFET is in saturation, the current I reference is equal to Kn dash W by L of M1 VGS minus VT whole square. The current I naught in this MOSFET M2 is equal to Kn dash W by L of M2 VGS minus VT. If the voltage at this point at the drain terminal of M2 is such that the M2 transistor is also in saturation, then this equation holds true. Now if we take the ratios I naught by I reference, which is equal to W by L of M2 time divided by W by L of M1. So the ratios of W by L of M2 and W by L of M1 is the ratio of the current, output current by reference current. So the same thing we are going to use in this circuit. Here this is PMOS and these are NMOS. The 1 milliampere current is being passing through this MOSFET, and this MOSFET will mirror this current here, but the current here will be equal to the ratio of W by L of these two transistors time this reference current. So here the current will be equal to 10 milliampere. So that 10 milliampere current will be acting as a current source for this NMOS transistor, and that will be mirrored here in this NMOS transistor. So this 10 milliampere current will be mirrored here as per their W by L ratio, which is now half of this current, because the W by L of this is equal to 10 and W by L of this is equal to 5. Similarly here, this PMOS is also mirroring the current from this MOSFET, and here the current will be 7 milliampere. 7 milliampere, why? Because the WL of this MOSFET is 7 and W by L of this MOSFET is equal to 1. So here current will be equal to 7 times of this current. Now apply KCL at this node. The incoming current is 7 milliampere, outgoing current is 5 milliampere. Here 2 milliampere current will go in this branch and make a voltage drop of 2 volt across this 1 kilo ohm resistance. So the option B is correct. So now we take the question number 3. In the circuit shown below, V1 and V2 are bias voltages. Based on input and output impedance, the circuit behaves as. And the circuit is shown below. In the circuit, we have this as a PMOS, this as NMOS. This is the alternating voltage source and having internal impedance R1. So in order to calculate the input impedance and the output impedance, we need to replace the transistors by their equivalents, small signal equivalent circuits. So let's replace the NMOS transistor will be replaced by an equivalent circuit like this. GM time VGS of NMOS. This is the internal impedance of voltage source, and here is the alternating voltage source. In a small signal equivalent, the all the DC voltages will be replaced by the short circuit. This is V1, which is replaced by the short circuit. It is connected here, and the current IG will be equal to 0. Similarly for PMOS, this is GM time VGS for PMOS. VDD is grounded, and the voltage V1 is also grounded. This is our source terminal. So VGS for this PMOS is equal to 0. So the current here will be equal to 0, which is dependent on VGS-P. So this will be equal to 0. Let's say the voltage here is Vx. So the current which will be flowing from this branch will be equal to GM time VGS. VGS is equal to minus Vx. So the current will be flowing opposite in this direction. This current is equal to GM Vx. So if the current which is flowing in this branch is equal to GM Vx and the voltage across this branch is Vx, so the impedance which will be seeing from this direction will be equal to 1 by GM, which will be equal to 1 by GM because the current is GM Vx and the voltage across this branch is equal to Vx. So the impedance will be 1 by GM, which will be present here by looking inside of the circuit. By taking internal impedance into account, the total input resistance or input impedance will be equal to 1 by GM plus R1. Now we take the output impedance into account by looking into the circuit from this direction and applying a test voltage. If we take the small signal equivalent of this circuit, by putting V in is equal to 0. If we see here, when we put V in is equal to 0, in that case this current will also become equal to 0, and if we apply a test voltage here, V test, the current here I test will be equal to 0, because the current source here and here both are 0, and when the current source is equal to 0 it will be replaced by an open circuit. So the output impedance will be equal to V test by I test. If I test is equal to 0, then this will be equal to infinite. So now come to the options. Current controlled current source is having input impedance equal to 0 and output impedance equal to infinite. Current controlled voltage source is having input impedance equal to 0, output impedance equal to 0. Voltage controlled current source is having input impedance is equal to infinite and output impedance is equal to infinite, and voltage controlled voltage source will be having input impedance is equal to infinite and output impedance will be equal to 0. So now the option A is correct. Now consider the question number 4. If the cut-in voltage of the diode is 0.7 volt, then the transfer characteristics of the below circuit is. In this circuit, the diode D1 and D2 are connected in parallel, but they are in opposite direction. The voltage source 1 volt is also connected to the p-type semiconductor or the anode of D1 and cathode or n-type semiconductor of diode D2. So if we apply the voltage Vi, which is greater than this volt, then the diode D2 will be forward biased and this will be reverse biased. If I apply Vi greater than 1 volt, then diode D2 will be forward biased, D1 will be reverse biased, but the diode D2 will not be conducting because the cut-in voltage of the diode is 0.7 volt. So if I increase the voltage Vi to 1.7 volt and make it greater than 1.7 volt, the diode D2 will be conducting and D1 will be reverse biased, so it is open circuited. So the diode D2 will be replaced by a voltage source or a equivalent voltage source of 0.7 volt, and diode D1 is open circuited, so it is not represented here. So now the V1 is Vi is here and V0 is here. So Vi is here and V0 is here. So if I apply the KVL in this loop, the Vi voltage will be equal to 0.7 volt plus V0. So V0 will be equal to Vi minus 0.7 volt. This is the equation of straight line. It is having a slope of unity beyond this 1.7 volt. Now if I apply voltage Vi less than 1.7 volt, diode D2 will be open and D1 is also open. The voltage V0 will be equal to 1 volt. If I apply voltage Vi which is less than 0.3 volt. This will make diode D1 forward bias and D2 is reverse bias. So now the equivalent voltage of D1 will be 0.7 volt. Here is 1 ohm resistance and this is 1 volt cell. Output voltage, here input voltage. If I apply the KVL in this loop, VI will be equal to minus 0.7 plus V naught. So V naught will be equal to Vi plus 0.7 volt. This is again a straight line equation having slope equal to unity for voltage Vi less than 0.3 volt. So if we see the options, for less than 0.3 volt, the slope is again unity. For 0.3 to 1.7, for 0.3 to 1.7, diode D2 and D1 both will be open and the output voltage is raised to 1 volt. Beyond 1.7 volt, again the diode D2 will be forward biased and the output voltage will be following the straight line equation of slope unity. The slope here is unity. So out of these four, this option seems to be correct. Thank you very much.